According to the expectation value, average value theorem, one of the postulates of quantum mechanics, the average energy is equal to psi h cap psi. This is in the bracket notation. This is also written in the integral form where d tau equal to 4 pi r square dr. In the case of helium atom, for hydrogen atom, there is only one electron, whereas in the case of helium atom, there are two electrons. Therefore, T tau 1 for electron 1, T tau 2 is for electron 2. Therefore, the integral is double integral.
Good morning. Let us study today variation method. Application of variation method to helium atom. How variation method is applied to solve multi-electron atom such as helium atom. We have already studied the variation theorem, variation method, variation principle. What is variation principle, etc. There are 4 steps involved in variation method for solving multi-electron atom. The Schrödinger wave equation of multi-electron atom cannot be solved fully because of the inter-electronic repulsion term we have studied in the previous class. Okay, now there are 4 steps. Let us see here. Choose the trial wave function. Let us, because of, for example, helium atom consists of 2 electrons, the Schrödinger wave equation cannot be solved exactly because of this term. We have already seen. Therefore, the wave function is not exactly obtained. Only for hydrogen atom, it is the Schrödinger wave equation is exactly solved. The wave function is obtained. The wave functions are nothing but atomic orbitals. The wave functions are nothing but called atomic orbitals. Therefore, the trial wave function of helium atom is obtained from the hydrogen atom oneness atomic orbital wave function. For example, we have already solved for hydrogen atom. This is the wave function of one electron, the oneness orbital, because in hydrogen atom oneness 1, in helium atom oneness 2. Therefore, 2 times it is the product of psi oneness and psi oneness. Therefore, this we have already seen the wave function for oneness orbital z cube by pi whole 1 by 2 e power minus z r1. For this is for one electron. You just repeat z minus z r2. There are 2 electrons. Therefore, the wave function, the trial wave function is a function of r1 and r2. That is z cube by pi e power minus z common r1 plus r2. Okay. Now, for helium atom, there are 2 electrons. Therefore, the Hamiltonian operator, actually in variation method, the second step is to evaluate the integral, evaluate the energy integral to obtain the average value or expectation value. According to expectation value theorem, average value theorem, one of the postulates of quantum mechanics, E is equal to, in bracket notation, it can also be represented in integral notation. Therefore, h cap equal to, for helium atom, the Hamiltonian operator is constructed. We have already shown, please see the video, we have already shown in atomic units. Okay, here delta 1 square is the kinetic energy term for electron 1. Delta 2 square is the kinetic energy term for electron 2 and potential energy term for electron 1, and this is potential energy for electron 2, and this is the inter-electronic repulsion term. R12 is the distance between the electron 1 and electron 2. Therefore, there are 5 terms involved in it. Let us substitute, evaluate the integral. Let us substitute this h cap, you know psi also, the trial wave function. Psi h cap psi equal to, this is in bracket notation, minus 1 by 2 psi del 1 square psi. Similarly, minus 1 by 2 psi over psi del 2 square by del 2 square psi minus 2. You take out 2 psi r1 psi 1 by r1 psi. Similarly, this and similarly psi r1 2 psi bracket notation. Okay. The del square is the Laplacian operator. The del square is the Laplacian operator. It is expressed in spherical polar coordinates. In spherical polar coordinates, 1 by r square dou by dou r, just invert r square dou by dou r, plus you will have theta term and phi term. But the trial wave function, since the trial wave function, remember, the trial wave function depends only on r. The trial wave function does not depend on theta and phi in spherical polar coordinate. Therefore, the only first term in spherical polar coordinate is considered. The other terms are not considered. You please write in your, please write that also. Okay. Let us now evaluate the first integral. First integral. This is the first integral minus 1 by 2 psi. Okay. Therefore, psi del 1 square. Therefore, 2 times it will come. Psi. Therefore, this is one side, another side. Therefore, z cube by pi whole square. Okay. E power minus z r1. Next for electron 1 r1 square 1 by r1 square 1 by dou by r1 square dou by r1 e power minus z r1 into d tau equal to 4 pi square dr. I have already shown. Therefore, 4 pi r1 square dr1 into integral, double integral, because there are two electrons. There are two electrons for electron 1 and for electron 2. The integral is for electron 2, therefore e power minus 2 is at r2. This is for electron 1, delta 1 square. Okay, therefore, this is simply e power minus 2 is at r2, 4 pi square, r2 square dr2. On evaluating this integral, on evaluating the first integral, the kinetic energy of first electron is equal to z square by 2. Okay. Similarly, for the second term, the second integral is evaluated for electron 2 kinetic energy. So similarly here, you just put z cube by pi whole square e power minus r2 here. r1 2 square or dou by dou r2, because this is for second electron. Therefore r2 square dou by dou r2 square minus e power minus r2 4 by r2 square dr2. Here e power minus 2 is at r1 4 pi square r1 square dr1 square. Again, on evaluating the integral, z square by 2 is obtained. Okay. Similarly, the third potential energy term for electron 1 is evaluated minus 2. Here you see minus 2 is 2 times, since you write 2 times psi. Therefore, z cube by pi whole z square. This is constant. Let us take it out. Then integral e power minus z r1. We are differentiating with respect to only integrating with respect to dr1. Therefore, z cube by pi whole square is constant. It is taken out. E power minus z r1 1 by r1 e power minus z r1 4 by r1 square dr1. And for this is for our second electron. E power minus 2z, similarly here, because for electron 1 4 pi r2 square dr2 equal to, on evaluating the third integral, minus 2z value is, the value minus 2z is obtained. Okay. Similarly for the fourth term, the potential energy for electron 2, same by 2 minus 2 e power minus z r2 1 by r2 e power minus z r2 4 by r2 square dr2 and into integral e power minus 2 z r1 4 by r1 square dr1 equal to, again on evaluating the fourth term, the value minus 2z is obtained. Okay. So next, the fifth term, fifth integral, that is for interelectronic repulsion. This integral is more tedious. It involves more mathematical steps. Let us not go into the mathematical steps. On solving the fifth term, Interelectronic repulsion integral term 5 by the value 5 by 8 Z is obtained. Now let us substitute in this expression. Okay. All 6, 4, 5, 6, 7, 8 in equation energy expression here. Okay, 3. Okay, therefore E equal to 2 into 2 times. Okay, here 2 times Z square by 2 plus, because we have already taken minus term here, taken into account of minus, therefore plus 2 times minus 2Z. Okay, plus the fifth term 5 by 8 Z. Therefore the energy expression is now obtained equal to Z square minus 27 by 8 into Z. This is called equation 1. Now the energy, according to variation principle, the energy obtained is always greater. The energy obtained is always greater or equal to E naught. That is the energy according to variation principle. The energy obtained by variation method is always upper bound. This is ground state energy. This is upper bound. Okay, this is, for example, here this is E naught. Okay, and this is E, variation method. Therefore, E is always greater than its upper bound to ground state. Therefore, minimize the energy to make it minimum, to make the energy minimum, minimize the energy, okay, minimize the integral or minimize the energy with respect to the variable parameter. What is the variable parameter? Z is the variable parameter because you see 2Z, therefore on differentiating 2Z minus 27 by 8 equal to 0. This on simplification Z equal to 1.69 is obtained. You see the Z value is only 1.69, whereas Z value is effective. This is the effective nuclear charge is 1.69, whereas Z value is equal to 2. Z value equal to 2. This is because in the helium atom there are 2 electrons present in 1s orbital, 1s2. One of the electrons screens the other electron. Therefore, the effective nuclear charge is less than 2. That is obtained here 1.69. That's why Z is a variable parameter. Z is considered as a variable parameter in the variation method. Okay. Now substitute Z value in 1. Z value in 1. Then this is the trial wave function. Now the optimized wave function. Z value put 1.69. The optimized wave function is obtained. Similarly, you put Z value in this expression. Okay, so when Z equal to, you put this value in this expression, the E value is obtained. The E value is obtained by this. Okay. Therefore, the optimized variation energy is equal to, on putting Z 1.69 in this equation, minus 2.8478 atomic units in terms of atomic units. One atomic unit, according to atomic physics or computational chemistry, one atomic unit equal to 27.2 electron volt. Okay, 27.2 electron volt. On substituting here, the variation energy obtained for the ground state of helium atom is minus 77.48 electron volt. From first order perturbation theory, using first order perturbation theory, similarly we can obtain the ground state energy by using perturbation method. The ground state energy obtained is minus 74.80 electron volt, whereas the experimental ground state energy is equal to minus 78.986. This is lower, you see, this is 77 upper. Okay, so according to variation principle, the energy obtained is always upper bound, is always greater than the ground state experimental energy. Okay, now in this case, you see this value, the variation energy is very close to the experimental value, whereas the perturbation theory is less accurate. This is there is more discrepancy, there is more difference, whereas the perturbation energy is very much close to the ground state energy. Therefore, the variation method is more accurate than perturbation method. This is often asked. What is now correlation energy? The correlation energy is the difference between variation energy and the ground state energy. This is equal to correlation energy. This is obtained. I have explained the correlation energy in the next slide. Please watch. Thank you for watching.
Let us see here what is correlation energy. For example, electrons tend to repel each other. So they will stay away from each other. That is, their motions are correlated. This correlated motion reduces the energy of the system, which is not actually considered in the variation method. Because of the correlated motion, that is electron correlation, the electron-electron repulsion is considerably reduced. Therefore, the correlation energy is defined as a measure of how much the movement of one electron influences the motion of other electron.